Alright guys, in previous video, we showed the exact solution for the synaptic weight and the bias. So we can find the optimal weight and the bias and use these two equations. So it sounds very easy or very straightforward, but actually this approach doesn't work for most cases because two reasons. Reason one is for a relatively simple system, this calculation could be time consuming and memory consuming. But if the system is complicated, for example, if we have multiple input, this solution basically is really hard to solve. So that means for the exact solution, it doesn't work. So we can figure out another way to find the synaptic weight and bias. That's using the searching approach. Through searching. Okay. What does this mean? This means we can give the weight from an initial random guess, that is W0. So we can start from any random initial guess, and then we can update the weight through adding an adjustment, the delta W. This is an adjustment on the weight, for example. This one is the initial guess, could be any random value. And this one is the updated weight. So after we update the weight, this is our goal. We want the cost function from the updated weight is less than the initial guess, which means after we do the update, the weight can provide a better result, which can make the cost function decrease. So we can run this process again and again. For example, at n times or the n iteration, this is the weight, and then we add a adjustment. We got the updated weight, which can make sure the cost function at the updated one is less than before update. So this is the initial thought through the searching approach. So this is the example we showed in previous example. For example, this is the initial guess. We know their cost function have a relatively large value. This one is epsilon 0. The value is large. And then we run this searching approach again, make them go to this direction until reach the minimum cost function, because this weight is the optimal weight. So it looks like not that efficient, but it works. It can go converge to the minimum value. So now the problem becomes to like, how can we find the adjustment delta W? Because here we know the updated weight equal to the current weight plus the adjustment. Now the problem becomes to how can we find the adjustment? So about the adjustment, there will be two factors can determine the adjustment. One is the direction, okay, could be the sign. Another one is the number or the step size. So this, if we know the two factors, we can find the delta W. What the sign means? Mean either positive value or negative value. This is the sign. And step size is you want to do is plus 0.1 or minus 0.1. So this will be, if you know the sign and you know the number, you can know what will be the updated weight. So we need to determine two things. One is the sign, another one is the number, the value, we can call that one. So if we can determine this one and this one, we can know in which direction we can adjust. We should adjust the synaptic weight. So the first one is how to find the direction of the delta W. So for example, here we know at the n, the cost function equal to this value. And after update, this is their cost function. And we know you do the adjustment direction is go to this direction, not up, but going down, go to this direction. This is adjustment direction. So basically, for this plot, this one is nothing but the slope, right? This is slope. So if we know the slope, we know the slope equal to the epsilon wn plus 1 minus epsilon wn. This will be the y directions along this direction. And then over wn minus 1 minus wn, this will be along the w direction. And this one over this one, that is the slope. So this is based on the plot. We know, okay, we can find the slope. That's the direction we are going to change the weight. And mathematically, that is nothing but the gradient operator. So we can just find the gradient. So here we have multiple w. So let's just find the gradient of cost function respect to different w, this different weight. So this is how can we find the direction of the delta w. So if we know this is their cost function, that's equal to 1 over 2 e squared. And we know e is nothing but equal to d minus y. And we know d is the desired response and y is the actual output. And for the cost function, we do the derivative according to w. That equal to 1, do the derivative of 1 over 2 e squared. This one going to equal to e multiply with delta e and delta w. Since we know e equal to d minus y, we plug this one into here. We got that's one equal to d minus y, and the plus e as d minus y here. So this equation going to become to this equation. And then we need to do a derivative of this guy respect to w. Since we know d equal to d and y equal to nothing but equal to xt and multiply with w. Therefore, we do dy and dw that equal to this guy and dw that equal to x transpose. So now we find the direction equal to gradient of cost function respect to w. Now we know the direction of the adjustment. The second thing is, how can we find the step size? So that is another thing we need to figure out, because if you go back to this slides, we know there are two things can determine the adjustment. One is direction, that is what we derived, and next one is step size. How can we find the step size? So there are basically two approaches. One is a simple one, another one is a complicated one. So for the simplest approach is for a fixed value, the eta. It's a fixed step size, or called the learning rate. So just choosing a eta, that's good enough. Of course, there has its advantage and has its limitation. The advantage is simple, just find a value. That one is the step size or the learning rate. It's very, very simple, very, very straightforward. But the limitation is it is not easy to find the optimum constant. So what does the optimum means? Look at here. We have different options. For example, we choose a very small eta. So this is the first cost function with the weight. And then you do the adjustment. It's moved to here, cost function. And then you keep updating the weight. So you will see it doesn't change much. That means it takes a really long time to really reach this point. So it is okay, safe, but not very efficient. The second one is choose a relatively big eta. What's going to happen? That is the every time it's going to change a lot since we have a large eta. So from the epsilon 1 to epsilon 2, from E1 to E2, that's a big jump. Since the eta is a fixed value, for next point, it's going to move to this side because the distance change from 1 to 2 and from 2 to 3, they are equal to each other. It's from there, jump to here, and then jump to here. So next step, you jump back, and then jump back to here, and then you jump back. It's always like a ping pong ball, bouncing up, but never really can stop at some point, can really stop at this point. That means, use terminology, that means it never can converge to a point, to the optimum point. So the second approach is using called the learning rate annealing function. We will learn this later in more details when we writing our MATLAB code. So this one is kind of like a adjustable cost function or adjustable learning rate. So for example, we start from relatively large value, and then with the increase of the iteration times, the adjust factor or the adjust step size is going to decrease. So that can give us relatively stable and at the very beginning it's very fast and later becomes a stable way to find the adjustment.